Patakit, and I'll be talking about Lab 2, projectile motion. What's the purpose of the lab? The purpose of this lab is to observe how an object moves as it is thrown into the air and follows a projectile trajectory. Additionally, we will observe the differences between the experimentation results and the computational model's predicted trajectories, with and without drag. Let's talk about some physics first. Newton's second law. We learned from last lab that the rate of change in moment is equal to the vectorial sum of forces on the body. Following this, we can then derive the velocity update formula, similar to lab 1. Another physics principle we need to know is the gravitational force. Fg is equals to g m1 m2 divided by r squared. Since on Earth the mass of the Earth and the radius is constant, we can replace it with Earth's gravitational constant of 9.8 meters per second squared to get F equals mg. Another physics principle we need to know is drag. We will use this equation for drag. B, some constant, times velocity squared. In our case, drag is proportional to the velocity squared, but it could very well vary in other cases, such as when the fluid moves in laminar or more turbulent flows. So, what are the experiment steps? First, we record the video of the paper ball in projectile motion. Second, we upload the video into Tracker and track the ball's position. Third, we graph the experiment's results in Excel. Fourth, we create a computational model of the paper ball with GrowScript. 5, we graph the computational results in Excel. And lastly, we compare the experiment and computational results with and without drag. Now, let's go over the conditions and setup of the experiment. The object we'll be tracking is a crumpled up paper ball. Once the video starts, the ball will be thrown with a small initial velocity and allowed to follow its projectile motion until it reaches the ground. Let's take a look at the video. Now, let's track the cart's movement. The red dots you see on the screen is what is being tracked. Next, let's look at the GrowScript. The ball's original position is measured by the rulers on the ground and the wall. Velocity and drag coefficients are chosen to fit the experimentation results. Since the tracker measures in intervals of thirds of a second, that's what we use for delta t. We calculate the net force by summing up the gravitational and drag forces. Then, we update the velocity using the velocity update formula. And finally, we update the position. We remove the line underlined in red for the case with no drag, and here are the visuals. The experiment and simulation results match quite nicely. The orange points, the simulation with drag and gravity, and the blue points, the experiment, line up to form a nice downward parabola. Additionally, we can see that the green points, in the case without drag, the ball moved a lot further and higher than the case with drag. Some possible sources of errors are that we are unable to calculate the true starting speed of the ball. It's hard to calculate the speed with such a low frame per second camera, not allowing us to take a very small time interval to measure its velocity. Also, we cannot just start measuring from the beginning up until the end, because even though it would make our calculation more accurate, we would not be accounting for the drag force constantly acting on the ball. Finally, there may be some tracking errors which may cause some errors in the position. So, let's talk about some what ifs. Imagine if the object were initially thrown up straight, with the same initial speed as in the experiment. Would the time this object takes to reach the ground be the same, longer, or shorter? Assuming that the ball was thrown straight up with the same magnitude of velocity, it would take longer. This is because some of the horizontal velocity was swapped for a vertical velocity, and so the total vertical velocity is higher and then it takes longer to reach the ground. Finally, what do the results mean? Does the object reach terminal velocity? No. None of the trajectories reach the point where the slope is constant, i.e., it has constant terminal velocity. Designing an experiment where the object reaches terminal velocity would involve dropping it from a higher elevation and allowing it enough time to reach terminal velocity. Thank you so much for your time.